So in this video, we're going to show an example of finding a general solution for a Bernoulli equation. So the first step is to actually verify that you have a Bernoulli equation. You can't use a technique if the differential equation doesn't have the form the technique applies to. So in this case, we have dy dx. We have the opposite of y, or minus y. So this would be a case where p of x is equal to -1. So -1 times y. And then e to the x times y squared. So we have p of x equals e to the x. So it does have the form of a Bernoulli differential equation. So we're going to go ahead and solve it using the technique for the Bernoulli equations. So start by rewriting the differential equation. We have dy dx minus y equals e to the x y squared. And for a Bernoulli equation, what we want to do is multiply both sides by y to the opposite of whatever the n is on the exponent. So this is a 2, so we're going to multiply by the opposite of 2, which is -2. And we do that on both sides. And as long as y isn't equal to 0, y squared times y to the -2nd power is just 1. Because we get 2 minus 2 is 0, we get y to the 0, and y to the 0 equals 1 as long as y isn't 0. So we just get an e to the x on this side. And over here, distribute the y to the -2 into the parentheses. We get y to the -2nd power dy dx minus y to the -2 times y to the 1 is going to be -2 plus 1 is -1. We get y to the -1 right here. And then once we get it into this form, what we want to do is try to linearize this term, the term that doesn't have the derivative, the y to the stuff. And we linearize it by taking w to the first power, which is just w, a linear term, and setting that linear term equal to y to the -1st power. And we're going to make that substitution here, but first we need to figure out what dy dx is. So I'm going to take dw dy, take the derivative of both sides of this substitution with respect to y. So derivative with respect to y on this side is going to be the opposite of y to the -2. And what we need to know is what w prime equals dw dx is. We're going to linearize this in terms of w. So I need to take the derivative dw dy times dy dx. That product equals dw dx. So I need to take the derivative of y with respect to x. So using the chain rule or implicit differentiation, we take the derivative of y to the -1st with respect to y. Then we take the derivative of y with respect to x. And then I can multiply both sides by -1 to get the opposite of dw dx equals y to the -2nd power times dy dx. And dw dx, we can just replace that if we want to with w prime. So once we have these two pieces, we can go ahead and try to linearize the differential equation. We replace y to the -2nd power dy dx with the opposite of w prime minus y to the -1st power gets replaced with a w, and this equals e to the x. And then we multiply both sides by -1 to get a coefficient of 1 on the w prime term. So that's going to be plus w equals the opposite of e to the x. And when I look at this, what I want to recognize is I have a differential equation with the form w prime plus p of x w equals q of x, a first order linear differential equation which we can solve using an integrating factor. So in this case, we want to notice that p of x is equal to 1. So our integrating factor is going to be u equals e to the antiderivative of 1 dx, which is just e to the x. And then we use the technique from the previous homework assignment where we solve linear first order differential equations using an integrating factor. So the technique is to multiply both sides of the equation by the integrating factor. when we distribute the integrating factor into this term, if we've done things correctly, it's going to be e to the x times e to the x is e to the 2x. If we've done this correctly, what we get right here for this expression is just going to be the derivative of the integrating factor times w. And the way you check your work is you differentiate this using the product rule. So e to the x times w prime, e to the x times w prime, plus the derivative of e to the x is e to the x times the w. So you just check that this is the result of taking the derivative of the integrating factor times w. And as long as it is, then you probably haven't made a mistake. And then to cancel the derivative, we're going to take the antiderivative. The antiderivative of the derivative of e to the xw is just going to be e to the xw. We're taking the antiderivative with respect to x. We have to integrate both sides. We do the same thing to both sides, and when we integrate, we get a constant of integration. So here we wind up with e to the xw equaling the opposite of the antiderivative of e to the 2x is negative 1/2 e to the 2x. We need that 1/2 so that when we take the derivative of e to the 2x, when we apply the chain rule to the inside function 2x, when the 2 comes down, it kills it. 1/2 times 2 is 1, so we just get the negative 1 that we have here on the previous line, plus our constant of integration. And then to get the w by itself, I can multiply both sides by e to the opposite of x. Multiply both sides by e to the opposite of x. E to the opposite of x times e to the x is 1. So we get 1 times w is w equals, distribute into the parentheses, so we get negative 1/2 e to the 2x times e to the opposite of x is just e to the x, plus c e to the opposite of x. And so we've got this solved for w, but we have to remember that way back here we made a substitution, so w really is y to the negative first power equal to negative 1/2 e to the x plus c e to the x. So if we wanted to solve this for y, we'd have to do a little, oops, I left the negative off. We would need to do some manipulating. So for example, I'd say I could stop here if I wanted to. That would probably be okay. But I could also multiply both sides times a y, which would leave me with y times y to the negative first is just 1 equals the stuff times y. And then if we divide both sides by the stuff, we will get y by itself. So we have negative 1/2 e to the x plus c e to the negative x, and we could divide both sides by that to get negative 1/2 e to the x plus c e to the opposite of x. And that would be an explicit solution for y. And I think we could clean this up a little bit if we wanted to get it into a cleaner form. Not too big of a deal. A little bit of algebra could get this a little bit cleaner. There's some things we could have done here, for example, like find a common denominator, multiply by 2 over 2. But 2 times c is just a c. So we could have written this as c e to the negative x minus e to the x all over 2, which would make it easy to take the multiply by a reciprocal on both sides to isolate the y. So there's some things that we could do to clean it, but this is the general gist of the solution process.